Hi, my name is Christine Chen, and I'm a staff member at Space Telescope Science Institute. I am the JWST Science Policies Group lead. So I run the Time Allocation Committee, in addition to other things, for Space Telescope, which is the Science Operations Center. I've been asked to talk to you today about JWST in the context of exoplanets and disks. So I'm going to give you an idea of where JWST is now, what you can expect to see in terms of some of the cycle 1 approved observations, and what the schedule is beyond for launch and beyond. This is a quick chart just showing the JWST status presented by Eric Smith at the European Astronomical Society meeting very recently. So you can see for the observatory that all observatory post-environmental testing deployments are complete. The final stow and preparations are underway prior to shipping. For science and operations, there is ground segment testing and operations rehearsals that have restarted, in addition to, or composed of completed launch readiness exercises number 3 and 4 and commissioning rehearsals. So LRE4 saw more mission operations center room staffing at Space Telescope in the Muller building. The thing that you may be most aware of is the cycle 1 program definition. So last year, ST had the call for proposals for JWST cycle 1. The proposals were due in right before Thanksgiving. The TAC met at the end of February, the beginning of March, and the program was announced in April. So this completes all of the hours that are available in cycle 1. There are 10,000 hours between the cycle 1 general observer program, which is what was defined by the TAC, the early release science, which was defined much earlier, and the guaranteed time observations. Programmatically, JWST is on track to complete the observatory for the August ship date and the October 31st launch readiness date. And NASA is working with ESA and Arianespace to be the third Ariane 5 launch this year after they returned to flight in late July. So I wanted to emphasize that exoplanets and disks are a really important science area to JWST. This pie chart here shows you the distribution of general observer cycle 1 approved programs by science category. And you can see exoplanets and disks in there in that yellow wedge at 23%. Just so you know, when the proposals are ingested by Space Telescope, they are divided by science category, each one of these science categories, which match the expertise of the JWST time allocation committees. So each committee, or each panel, sorry, within the TAC is allocated a number of telescope hours for small and medium proposals that the panels select. The panels have panel chairs, and together all the panel chairs make up the executive committee that then selects the large treasury and archival legacy programs based on external reviews and advice from panel members. The next two charts are just a quick reminder of the different instrumental capabilities on JWST. So the imaging modes and the spectroscopic modes. So here you can see the imaging modes, and the bars show the various instruments, NIRCam, MIRI, and NearInfrared, and the wavelengths that they cover. And you can see along the left the different modes, standard, chronographic, and more standard modes. So today I'll be talking about some of the chronographic modes and aperture masking interferometry. And then here's a slide showing the spectroscopic modes, again, from the 4 instruments. In particular, with the exoplanet observations, there is a lot of use of the time series observations. These are slitless instrument modes. So on the bottom, you can see that there are slitless modes for NearInfrared, NIRCam, and MIRI. And you can also see some other modes that are relevant for this science area are the IFU. So the IFU basically provides integral field spectroscopy, so spectroscopy at every point in the field. And you can see that there are 2 IFUs on JWST. There is the NIRSpec IFU that goes to 5 microns, and the MIRI MRS IFU, which goes beyond 5 to about 30 microns. So in the presentation today, I've given you a little bit, a very fast introduction into JWST. I'm going to move on and spend the bulk of my time talking about approved JWST Cycle 1 observing programs, mostly broken down into 4 categories, characterizing dust and gas and protoplanetary and debris disks, searching for exoplanets and disks, characterizing the surfaces and atmospheres of exoplanets, and because there is some synergy, also characterizing the surfaces and atmospheres of solar system bodies. I'll also tell you about the JWST Cycle 1 timelines and give you some resources to learn more and get ready for JWST. So moving on to some of the science programs, I'm going to start with disks and move to planets in the solar system as was described in the outline. JWST is expected to enable some very exciting observations of protoplanetary and debris disks, both of dust grains, so solid state material, and also gas phase material as well. The chart here shows in the inset a Spitzer IRS spectrum of, I think this is a class 1, class 2 protoplanetary disk. And you can see that there are a number of absorption features along the line of sight in this optically thick system. So you can see water ice highlighted in blue, methanol ice in red, silicates in that tan, and carbon dioxide in green. So JWST will reopen this area of wavelength space to provide the opportunity to study ices in these planet formation regions. So in addition to water ice and carbon dioxide, methanol that are pointed out in the diagram, methane and sulfur dioxide as well. These are other materials that are expected to exist in these disks. And because it is more powerful, that is more sensitive, it'll be able to look at fainter targets. There are a couple of very nice programs looking for signatures like these in everything from protostars to protoplanetary disks to characterize ices. So I've highlighted a couple of programs here. One is an early release science program by Melissa McClure called Ice Age, which does include a protoplanetary disk, and then a Cycle 1 program also from Melissa McClure, focusing on 2 of these edge-on protoplanetary disks where you can see the dark lane and then map the locations of ices. These really rely on using the NearInfrared and MearInfrared. Moving on, in addition to looking at the solid state, it'll be possible to also probe volatile gas in these systems, particularly gas that has temperatures of 500 to 1000 Kelvin and is located at distances within 5 AU of the stars. And so there are a number of programs that are designed to make these NearInfrared observations of gas phase emission to create inventories of major molecular species. So these are some of the same species that are being studied in the solid state as well, but now in the vapor phase. I'd like to particularly point out the very good synergy with ALMA observations. There is a D-Sharp MIRI Treasury Survey of Chemistry and Planet Forming Regions by Colette Salek et al. To use the NearInfrared to, again, map the locations of these hot volatile gases using the NearInfrared. And then there's another program that I've cited here by Klaus Pontoppidan to do a deep search for rare molecules and isotopologues. Both these programs have no exclusive access data. Moving on to slightly older objects, debris disks. Debris disks have been studied similarly using some of the same spectroscopic techniques as for protoplanetary disks, but also there are some scattered light programs that I'd like to talk about too. So for dust around stars, there are 2 ways to perform remote sensing. One is in scattered light. So this means that the starlight hits the dust grain and then is deflected, is scattered off the dust, and you see that reflected starlight. And the other is through thermal emission, where the star heats up the dust grain, and then you see heat from the dust grain. So the first part that I'm going to talk about here is the scattered light. So scattered light imaging has been done using HST and ground-based instruments. These observations typically reveal asymmetries in the disks that are indicative of the presence of planets. For the very stable space-based observations, they can find extended halos of small dust grains that are blown out of the system by radiation pressure. Or you can also measure the scattering phase function. That is how much light is scattered by the dust grain as a function of angle. So, whether the dust grain deflects the light a lot, so backscattering, so the photon comes in and bounces back the way it came, or forward scattering where it doesn't get deflected and it just continues on. I'd like to highlight that NearCam has medium band filters, and there's quite a bit of interest in trying to image in and out of some of the solid state reflectance features of ice and carbon dioxide. And I've cited a program here from the NearCam GTO team to look at these 5 nearby bright debris disks to try to study the morphology of the dust and the grain properties. In addition to studying debris disks and scattered light, as I mentioned, it's possible to also study their thermal emission. One program that I wanted to highlight for studying the dust and thermal emission is a program to study silicate emission features in the dust. So in this case, silicates have solid state emission features at 10, 20, and 30 microns. And these silicate emission features can be very diagnostic of the detailed grain properties. So they can provide information about the detailed composition. So whether you're seeing, for example, olivine versus pyroxene versus forsterite versus enstatite, and then the crystalline fraction. So whether or not the molecules are arranged into a lattice, as in the crystalline species forsterite and enstatite compared to olivine and pyroxene. And then they can also tell you something about the grain size based on the shape of the feature. The nearest debris disks, for example, like beta Pic, will actually be spatially resolved by JWST. So the middle picture is a T-Rex image of beta Pic at 24.6 microns. And you can see the NearInfrared channel 1 field of view for comparison. Because it's so spatially resolved to JWST, it will be possible to see how the silicate features change as a function of position in the disk. These kinds of experiments have been done in the inner disk from the ground using Subaru comics, and the bottom set of spectra show you spectra that have been extracted from different regions of the disk, focusing on 8 to 12 microns because that's the window in the atmosphere that we can work on from the ground. Analysis of these ground-based and STScI observations do indicate gradients in the iron to magnesium ratio, the crystallinity of the dust, and the size of the grains in the disk. So the example program that I've called out here is actually it's my GTO program to use the NearInfrared to study beta Pic. Moving on, an area of really growing interest in debris disks is exocomets. So there is some evidence that there are comets in other planetary systems, just like there are comets in our own planetary system. In this particular case, these debris disks are thought to be sort of maybe young to mature analogs of the solar system with very massive Kuiper belts. So repositories of comets that may be gravitationally perturbed into the inner part of the planetary system. These exocomets are seen as time variable redshifted absorption features. And so I've shown some data here that is for a particular star called HD 32297. So the postage stamp picture in the red and black, that's an HST scattered light image of 32297 with the millimeter contours from ALMA that are overlaid, showing the edge on disk and where the planetesimal belt is located. The figure to the right of that shows the CO first moment map. So showing that it is bright in CO, and that there's a disk in Keplerian rotation. And then after that are the individual channel maps. So that is the reservoir of comets in this particular system. And then the way the comets are seen, you can see in the vertical strip on the left, these are absorption spectra in sodium-1. You can see that they're redshifted, they're at a positive velocity. That indicates that the gas is moving away from us and toward the star. They're infalling to the star. And the feature is time variable, so it's changing as these exocomets are falling in. So there are a couple of programs that are planning to do NearInfrared fixed slit spectroscopy to look at volatile gases, or to try to look at volatile gases with this rather moderate spectral resolution in these exocomet systems. There are about 6 of them across these 2 programs that will be observed. So of course, one of the most exciting capabilities that JWST is going to enable is the detailed study of planets. So I'm going to start to shift toward planets and the interaction of planets and disks. So this particular chart shows the current phase space over which planets have been detected from the various techniques that people use to study exoplanets. So you can see mass on the vertical axis and separation on the horizontal axis, with the transit detections shown in orange, and as you move out, the radial velocity detections, and then finally direct imaging. So direct imaging is just what it sounds like when you're able to take a picture where you separate the star and the planet and can characterize the planet that way. RV and transit really rely on being able to, for example, with transit, look at when the planet crosses in front of or behind the star, and separate out the star signal from the planet plus star signal that way. So one of the really exciting things about JWST is that it's expected to open up a phase space that's shown with the red circle there. So essentially, most of the ground-based facilities and even space-based facilities that have done direct imaging so far have really been limited in the mass in which they've been able to probe down to. So for example, SPHERE and GPI, you can see get down to maybe a Jupiter mass for planets around nearby young stars. But JWST is expected to push down into the region of Saturn and Neptune mass analogs at wide separations. So these direct imaging observations will leverage a technique called high contrast imaging. And so I just wanted to say a few words about high contrast imaging before moving on. So because JWST has this very large aperture, 6.5 meters, it will be expected to spatially resolve exoplanets and disks around nearby stars. The problem, of course, is that the host stars are very bright compared to the companion or the disk. And so astronomers employ PSF subtraction in order to try to remove the glare of the host star so that they can characterize the planet or the disk. And so there's a rich tradition of using PSF subtraction algorithms, both from space and the ground. Depending on the environment, you may see different techniques used. Typically in space, people leverage reference differential imaging heavily, where you image your target and then you image a different reference star and then subtract the reference star from the target in order to reveal things around it. From the ground, there's been a lot of development in recent years in the use of angular differential imaging, where the telescope's allowed to rotate. And so the planet looks like it's moving in the detector frame, and that helps to remove the PSF. And also spectral differential imaging, in which the PSF changes its width because you're looking at different wavelengths. And so the planet stays in the same place, but the PSF changes size. And so you can leverage that information to perform PSF subtraction. So because this is going to be the beginning of the mission, there are not yet large repositories of PSF observations. And so in cycle 1, we expect that most programs will probably have to rely on classical PSF subtraction, where an observer pairs the targeted observation with a reference star and then performs the PSF subtraction. And in that particular case, it's useful to make sure, particularly in the near infrared, that the spectral type for the host star and the PSF are not too different from one another. So these coronagraphic techniques will be applied to studying, as I said, disks and companions around nearby stars. And I wanted to start off by talking about debris disks, because debris disks have a rich tradition of being associated with the discovery of companions. This is sort of a mini story, which is the mini story of sort of Beta Pictoris. So in the top figure, this is an HST ACS image of the Beta Pictoris disk. When these disks are viewed at high angular resolution, typically structures are seen. In this particular case, there's a secondary disk that's tilted compared to the primary disk. This structure is indicative of the presence of a possible perturber. When the structure was found, it wasn't known whether it was a brown dwarf, something massive that was close to the star at 3 AU, or something much less massive like a Jovian mass planet that was much further away, maybe 150 AU. And this was really resolved by ground-based observations. The next figure down shows you a VLT NACO composite image showing the discovery of Beta Pic B, seen at two different epochs. So you see the bright dot that's moving from one side to the other side of the star. The idea then is to image many debris disks or disks around young stars to look for the presence of planets. So again, a lot of these targets have structures in their disks that are indicative of dynamical sculpting by undetected planetary mass companions. And in cycle 1, JWST will observe 38 young stars and white dwarfs using these high contrast imaging techniques, particularly the coronagraphs, the NIRCam and MIRI coronagraphs, to search for and characterize exoplanets. And you can see in the bottom figure that is a simulated spectrum for a 1,000-degree companion, and how it compares to the large suite of NIRCam filters that are available for the coronagraphs, and the MIRI, the 4 MIRI coronagraphs. And I've listed here for your reference a couple of programs that are hoping to leverage this capability to search for companions. One is a GTO program led by Chaz Beichman on 3 of the fabulous 4, Fomalhaut, Vega, Epsilon, Eridani, and the bottom one is a GEO program by Seba Marino, focusing on HD 19945, 106, I think that's a 147, and 206893, using the MIRI coronagraph. In recent years, there's been a lot of really exciting work that's been done on protoplanetary disks. So now moving to objects of younger ages and finding evidence for sculpting of these disks by planets, particularly from ALMA. And one star that received a lot of attention in JWST cycle 1 is the Herbig AE star HD 163296. This object has been well studied using ALMA, both in the continuum and also in CO, in the gas. And so the image on top on the left, this is a continuum image, which clearly shows gaps in the disk. There are gaps at 0.1, 0.5, 0.9, and 1.5 arc seconds. And the 2 outer gaps are depleted in CO, suggesting that there may be giant planets in these gaps. In addition to the thermal continuum, the gas has also been studied in this particular system. And the bottom is a model that has been produced by Jehan Bai. And you can see the little tiny inset in the bottom right corner, which is the model image from his model. So in this particular case, the planet is embedded in this gap in the disk. And because it's massive, it impacts the flow of gas in the disk and can create a signature in the velocity of the gas. And so the top right image shows an ALMA 12CO channel map from this target HD 163296. And that structure is indicative of the presence of a planet with the planet overlaid there. And so there are 2 programs in JWST cycle 1 that are designed to try to search for and characterize this planet directly. So one with the NearCam chronograph by Luca Ricci, and then another one using the mirror chronograph by Kubno. I wanted to also point out that in addition to the coronagraphs, NearIS, the near-infrared slitless spectrograph and imager, has a very high angular resolution capability called aperture masking interferometry. Traditional single element telescopes have an angular resolution of 1.22 lambda over D. However, in this particular case, a mask is used in conjunction with the telescope, and it blocks out the light from many of the primary mirror segments, and then facilitates interference of the light from, you can see those 7 specific segments from the mask in the top left corner. This provides much higher angular resolution, half lambda over D instead, and so it provides the highest angular resolution mode on JWST. You can imagine that because it does block out, a substantial fraction of the light from the telescope, it is best for studying bright objects. And it's expected to provide a contrast of about 10 to the -4 at smaller angular separations compared to the chronograph, so 700 or 70 to 400 milliangstroms, or sorry, milliarc seconds. There's a program that I wanted to call out as an example of using the nearest AMI mode. And this is a program led by Doug Johnston, looking at protoplanetary disks, PDS-70, HD 100-546, and HD 135-344. These are actually transition disks. Transition disks are protoplanetary disks with large central clearings. Usually they're identified through SED modeling and the identification of sort of a large central clearing through the SED. So you see the SED at the top, flux is a function of wavelength with the starlight peak in the blue on the right and the thermal emission from the dust on the, the star on the left, the blue dotted line, and the thermal emission from the dust on the right. And so you see this sort of flattening to sort of dip around 10 to 100 microns or so. 10 to 100 microns, where that's the missing emission indicates that there is this gap. So there have been observations that have directly detected companions in this gap. So the bottom image shows the bottom right. This is a VLT sphere image showing the B and C components. And then also the corresponding ALMA data in which the B and C components are also detected. I'll just highlight PDS-70 as a disk that I think is one of the targets for which there's some disk modeling that's going to be discussed at the workshop. So clearly high contrast imaging is a really important technique for JWST. The community expects to use these modes to characterize exoplanets and disks. So I wanted to call out in particular one of the early release science programs. This is the high contrast imaging ERS program, which is led by Sasha Hinckley. All of the early release science programs have no exclusive access period. So that means that the data becomes public immediately. For this particular ERS program, there are several objectives. One of them is just remembering that HST chronography required numerous cycles to perfect and is actually still being refined. So it really takes a lot of effort to understand how best to interpret the chronographic data. And to really do the best science, we need the best understanding of the instrument response, PSF stability, and PSF subtraction. So this is a community-wide need. And given JWST's relatively short 5 to 10 year lifetime, the correct observing strategy and data processing methods, really have to be identified as early as possible. So this particular program will study both companions and disks. They've picked out a companion HIP 65426B, and they will study it with NearCam and MIRI chronographic imaging and the nearest AMI. On the top, you can see simulations from this group On the left is the Sphere 1.1 micron discovery image, and then their simulations for what the data will look like from NearCam at 4.3 microns and MIRI at 15.5 microns. And the bottom, that is a model of the atmosphere that's expected, the spectrum of the atmosphere that's expected to be seen, along with simulations for what the data points will look like from these observations. The current observations from the ground are shown with those orange bands. In addition, they will also study HD 141569, which is a young debris disk system, also with NearCam and MIRI chronographic imaging. And they'll also look at a wide separation companion, VHS 1256b, to try to understand what characterization of a distant companion spectroscopically would look like. So I'm going to shift gears a little bit and talk in a little bit more of a science-focused way about the science that JWST observers hope to achieve during cycle 1. So the plot on the left-hand side is a summary showing the targets that will be observed in the guaranteed time and general observer program. So the red dots and the orange squares compared to the Spitzer and HST observations, which are shown as white dots. And so you can see planet radius on the y-axis and equilibrium temperature on the x-axis. And so the large planets at the top, so the hot Jupiters that are close to the star, and the cold gas giants, which are far away from the star. And then moving to smaller planets, the lava worlds that are at the bottom left corner, and more like Earth-like planets on the bottom right corner. So what you can see is really that JWST will explore the diversity of exoplanet atmospheres across a range of size, temperature, age, and stellar environment. So there's a whole diversity of things that will be done, from several transiting hot Jupiters and a planet in the Neptune desert, to direct imaging and spectra of cold gas giants. So that was the previous program that we spoke about a little bit, studying sub-Neptunes and super-Earths with time series spectroscopy to look at this population in detail, to several young giant planets, including those newly formed in debris disks, as I already mentioned, 2 terrestrial planets that are so hot that they're balls of lava, planets transiting active M-dwarf stars, offering the best opportunity to explore the atmospheres of terrestrial worlds. So focusing down a little bit about the science goals for giant planets in particular, the plot on the left shows sort of the chemistry and thermal structure in the atmosphere of a giant planet. So the vertical axis is height or pressure, and you can see temperature along the x-axis. So some of the key things that JWST will do are to measure the presence of important molecular species, including the C to O ratio, which is thought to be very diagnostic of where planets formed relative to the snow line. So whether they formed beyond the snow line, which is thought to have happened in our solar system, or closer. In addition, there'll be a lot of detailed atmospheric studies to study the height and composition of clouds and hazes, how the atmosphere varies with longitude, and how the atmosphere responds to varying amounts of radiation. So you can see on the right-hand side of the cartoon, the impinging UV visual and infrared radiation, which can, for example, photodissociate molecules and ionize molecules as well. So how does that impact the atmospheres? So the second technique that will be very widely used using JWST for exoplanet studies is the transiting method. So the transiting method relies on looking at a star in the plane of the planet that's orbiting around it, so that the planet passes directly in front of the star in transit, goes around, and depending on where it is relative to greatest elongation, you first see crescent, and then at greatest elongation, the quarter phase, and then gibbous as you swing along the back to eclipse, where the star blocks out the planet, and then ingress into eclipse as you move into eclipse, and egress as you come out. And so there's really quite a number of transiting exoplanets that will be observed in JWST cycle 1, 68 of them, using a variety of instruments and modes. 25 of these have been discovered with tests. And you can see I've listed out the instrument modes that are most popular for transiting exoplanet work, and the number of targets that will be used for each of those, or will be observed with each of those modes. And the right-hand plot is a really nice figure by Nicole Cologne, which shows the sample of planets that will be observed in JWST cycle 1 again, but now as a function of technique for transiting exoplanets. So again, temperature on the y-axis, planet mass now on the x-axis, and you can see that there will be many targets that will be observed in transit or eclipse, and 3 targets that will have their phase curves measured. So just like the high contrast imaging community, the transiting exoplanet community has a very nice early release science program, again, with no exclusive access period to its data, to help the transiting exoplanet community learn how to use JWST. So its key objectives are to determine the spectrophotometric time series performance of key instrument modes, establish best practices for removing systematic noise, and provide the community with a comprehensive suite of data to demonstrate scientific capabilities. So the large plot in the middle shows you an example of a Spitzer IRS observation of a transiting system. And you can see a lot of high frequency structure in addition to trending. These are long-term drifts. So that's not real signal. That is due to a number of things. One is intrapixel sensitivity. So this means that it depends, the sensitivity of a pixel depends on where on the pixel you land. And so there are, for example, drifts by the telescope. And this is particularly important because the Spitzer instruments are undersampled. And so they're not Nyquist sampled where there are 2 pixels, for example, for every resolution element. And so these effects need to be corrected. And so you can see in the bottom part of that figure, once the instrumental effects are removed, then it's much easier to see the transit and the eclipse, and to see the slow frequency structure that is the thermal variation, which then can be inverted into a map for the heat distribution from the surface of the planet. So for this particular group, they have plans to focus on WASP 39b. So this is a nearby bright star with a giant planet, and to exercise the main TSO modes, NearIRS, NearCam, and NearSpec, and to try to understand the relative merits of them. They're also going to observe WASP 43b with the NearIRS, so now at longer wavelengths, from 5 to about 30 microns, and then they're going to explore a bright target WASP 18b using NearIRS sauce. Okay, so in addition to characterizing exoplanets spectroscopically using the transit technique, they can also be characterized using integral field units, using high contrast imaging techniques. So these are cases where now the star and the planet can be separated from one another, and essentially the target's placed on an IFU, and a spectra can be recovered for both the star and also the companion. There's a couple example programs of what this will look like. There was already listed in the high contrast ImagingERS program an example where the companion is quite far away from the star, and so the star doesn't end up in the field of view when you point at the companion. I've cited here a couple more programs that are kind of like this. The first one is actually a study of a brown dwarf companion to a main sequence star, in which the brown dwarf is sufficiently close that it will be in the IFU field of view. And this is an opportunity then to try to learn how to perform PSF subtraction using the NearSpec IFU. And then another program that was approved in cycle 1, a general observer program by Keelan Wilcombe, that is looking at this system Tycho 8998760-1, which is a multiple planet system using the NearSpec IFU and NearInfrared. And this is another situation where the planets are further away from the star, so the high contrast imaging aspects may be less important. So moving on to studying lower mass planets, JWST is going to provide the first comprehensive look at the composition and formation of planets 1 to 4 times the radius of the Earth. So these sub-Neptunes and super-Earths. The Neptunes with atmospheres composed of hydrogen and helium, and the super-Earths, which are originally really rocky objects. So NearSpec, NearInfrared are going to obtain transit spectroscopy of at least 12 planets that are smaller than Neptune, with the goal of understanding the basic composition, particularly the sub-Neptune atmospheres, looking for CO2 and CH4. And so you can see that there are actually 2 large programs that were approved in cycle 1 in this area. Large programs have no exclusive access period, so all of this data will become public immediately. So it's unknown whether terrestrial worlds orbiting active M stars can hold on to their primary atmospheres. One possibility is that the stellar activity, another possibility is that stellar activity from active M-type stars can contaminate exoplanet atmospheres. And so there's a large program that's geared toward looking at these low mass planets around M stars to understand the impact of the stellar host stars on their atmospheres. This is a program led by Kevin Stevenson that you can see at the bottom right corner. And so just for fun, a couple more programs focusing on low mass planets. So hot rocky planets. So there are many more programs than I'm highlighting today, but I just thought these were fun, partly because I think my impression is that these targets are ones that the community is particularly interested in, even if they fall a little bit outside of this year's workshop topic, which focuses on young planets. So hot rocky planets, to constrain past and present geology. There's a very nice program by Laura Kriegberg on LHS 3844b to understand, look for signatures of volcanism and study the geodynamics of the hot rocky exoplanet in that system. And then, of course, 55 Canker E has received a lot of attention. And there are a couple of programs to study this lava world to understand whether it has an atmosphere and whether it rains lava on the night side of these worlds. You can see there's one probing secondary eclipses with NearCam imaging, and another with the NearInfrared, and then a separate program that's now probing transits with the NearCam Prism time series, looking for silicon monoxide gas. One of the most exciting systems that's being studied today is Trappist1. This is an M-type star with 7 rocky planets in the habitable zone. These planets are all located very close to the star within the orbit of Mercury in our solar system. But because the M-type star is so much more luminous, the planets have much cooler temperatures that are similar from everything from more Mercury-like to more Mars-like. I just wanted to point out here that all 7 of the Trappist-1 planets are going to be observed in cycle 1, and there is a very nice community initiative that's described on AstroPH about how this planetary system could be studied comprehensively. And so I've listed out here all of the GEO and GTO programs and the particular companions that they are searching along with their modes, just out of interest. So the last science area I was going to talk about very briefly was our solar system, because as the nearest planets and reservoir of minor bodies, they provide a benchmark for our understanding of exoplanets and disks around other stars. I wanted to point out that nearly all of the large solar system bodies outside Mars and outside at larger radii are represented in JWST cycle 1. So the planets and their moons and then in addition, minor bodies such as asteroids, comets, and Kuiper Belt objects. So to give you a feeling for the complementary science that will be carried out on these particular objects, there's a lot of work that'll be done on Jupiter, Saturn, and their satellites, exploring below the visible cloud decks of the Jovian and Saturnian atmospheres to understand their weather systems and chemistry, to search for new moons and measure the surface compositions of the known moons. And so there's a list of some of the programs and what they will be studying. Of course, another item of interest is studying the hydrocarbon atmosphere of Titan. And again, there's a program by PI Nixon to carry this out. So these in general are, with the exception of the ERS programs that are listed in the middle, these are actually GTO, guaranteed time observations. There are a lot of guaranteed time observations for the solar system in cycle 1, and that community has elected to make all of that data public as soon as it's taken, so it has no exclusive access period. So moving on a little further, Uranus and Neptune. The ice giants Uranus and Neptune haven't been visited by probes with modern instruments. And so this will be the first time to obtain a full chemical inventory of their atmospheres using the IFUs, NearSpec and NearIFUs, at multiple locations in the disk, and to revisit to monitor atmospheric conditions. It's thought that these planets have moon systems that have been observed, and it's thought that these moons have been captured from the Kuiper Belt, for example, and so they should be very similar to Kuiper Belt objects. And so observations of the moons of Uranus and Neptune will be able to explore that hypothesis and determine how similar or different they are. And then finally, from our solar system, there will be a lot of study of asteroid, comets, and trans-Neptunian objects to understand the volatile content of these populations. Again, using the spectroscopic modes, about at least 20 asteroids, including the largest asteroid series in Pella, are going to be observed with JWST in cycle 1. And then these observations of Kuiper Belt objects, TNO, trans-Neptunian objects in the outer parts of the solar systems, will also be studied to survey down to 10 kilometers in size, and then also obtains spectroscopy to better understand the properties, including composition. And then comets, where you now have material going into the volatile phase, there'll be an opportunity to inventory the species from those systems. There's NearSpec and NearI observations planned for 12 comets to measure and then there's also a target of opportunity programs to study the next interstellar interloper. So my last slide in this section is just as a reminder that all of the approved programs are posted online, and so you can browse them to see all of the science that people will be conducting in cycle 1. And all of the programs that have no exclusive access period are specifically marked out as such. I just wanted to move to schedule for a little bit to tell you kind of what's been going on at the Institute and what to expect going forward. This summer, the Institute staff are conducting technical and scheduling reviews of the accepted programs. And you see that as the green block, the large green block in the middle of the timeline here. And this is in prep for, at the beginning of the fall, to review the calibration plan to make sure that there are appropriate calibration observations being taken. So these technical reviews and scheduling reviews by STScI staff are examining a number of issues, helping to refine the programs, but then also examining 2 issues from more of a community-wide stance. One is data volume. Some of the solid state recorder on board JWST is because it was locked in earlier in the design of the mission, has a somewhat limited capacity compared to the amount of data that JWST can actually take. And so some of the instruments, NearCam in particular, because it has 10 detectors, if they are read out rapidly and you want to save all the data, it can fill the solid state recorder very, very rapidly. So the programs are being looked at for data volume because some of these high data volume programs may not be able to support having parallel observations when you use another instrument at the same time to look at something else. Another issue is uninterrupted observations. So the unit of observation on JWST is called a visit. And there are cases in which specific visits need to be scheduled back to back. So in my mind, I'm thinking of coronagraphic programs in particular, in which you observe the target with the coronagraph and then the reference star. You don't want to break up those observations by repointing the antenna at the DSN to download the data, because as you do that, you change the thermal load on the telescope and it changes the wavefront. And so really what you want to do is observe the target and the PSF reference back to back to minimize the change in the PSF between the two observations, so you can do the best PSF subtraction. So these uninterrupted observations are only allowed when they're scientifically required. STScI recognizes that some programs are going to need adjustments because this is cycle 1 and we're all still learning how to use the observatory. And so these adjustments may lead to longer charge times, and STScI will be flexible in allowing these adjustments in cycle 1. I just wanted to show a couple fun graphics from ESA about launch and early parts of commissioning. So about 55 days before launch, JWST will arrive at Paria Cabo, the harbor in French Guiana for ESA's spaceport. And you can see the schedule here for assembly and integration, launch, and then ESA will track Webb through the early phase within the first 30 minutes of launch. So you can see all of the milestones that happen with the rocket. From there, JWST will journey to L2. It'll take about a month for it to get there, for the telescope to unfold and enter orbit around L2. There are 5 additional months of commissioning at that point. About half, it's divided almost equally between commissioning the telescope itself, the optical element, and then the instruments. Early on in this phase, there is some amount of waiting that happens for the telescope to become cold. So in equilibrium, the telescope is approximately 45 Kelvin. There are some parts of the observatory that are a little bit colder. For example, NearInfrared, because it looks at the longest wavelengths, has to have a very cold focal plane, 78 Kelvin, and it uses a cryocooler to achieve that temperature. So for half the time, the staff will be waiting for the facility to cool, and then we'll be phasing the mirrors. Remember, there's all the different segments, and when the mirrors first unfold, the primary first unfolds, there'll be spots of light from each individual segment that have to be phased so that the mirrors work collectively together as one. And then after that, there will be a period of a couple months for testing the instrument capabilities, making sure that things work as expected. And JWST has a lot of instrument modes, and so this will take some time. For example, MIRI, as I mentioned, the longest wavelength instrument doesn't even begin its commissioning until the last month of the 6-month commissioning period between launch and then when routine science observations begin. This here is the JWST science timeline. So it shows launch readiness on the left with the launch readiness date of October 31st, 2021. And the key dates here that I wanted to point out are, again, the start of cycle 1 science observations at L+6 months. And then when the cycle 2 call for proposals comes out and the proposals are due. So we anticipate the cycle 2 call for proposals to come out at launch plus 11 months, with the deadline at launch plus 13 months and the TAC meeting at launch plus 15.5 months. So this is part of, we anticipate offering JWST proposal opportunities every cycle in the mission. And then cycle 2 would start exactly 1 year after cycle 1 started, so at launch plus 18 months. A couple of just things to be aware of. STScI is offering data analysis training classes. These are the J webinars that provide hands-on instruction on common data analysis methods. They're virtual classes that are limited in size to 40 participants that give an opportunity to interact with the virtual programming environment. All of the materials are made available after the class. And you can see that some have already occurred, and there are some that are also in the future. If you want to register for a future one, you can see the URL there, or if you would like to explore the class materials online, they're also posted at that URL. In addition, there are some simulated TSO observations that have been posted on the website, and you can see them there. Particularly fleshed out are the TSO modes. So you can see that there are example data sets, simulated data sets for each of the TSO modes, and also for nearest AMI. And then I just wanted to make sure that everyone was aware that there is a JWST users committee. This has been constituted by Space Telescope and NASA Goddard to provide user community advice to the observatory as a whole. I've listed in the chart the names of all of the current JSTUC members. You can see that there are a number of people from the Exoplanet community that are currently serving on the JSTUC. And the JSTUC really welcomes the feedback from the astronomical community. So there are 2 ways to reach out to the JSTUC. One is that you can email the chair from the JSTUC website at that URL, or you can also reach out to the committee members that you see listed here. So this is my very last slide. And I just wanted to say that I am tremendously excited about the promise of JWST. And this is really a community effort. The telescope was built for the astronomical community, and only by use by the astronomical community can we maximize the science return from the telescope. So this picture here shows you the JWST mirror relative to the HST mirror, and you can see the pictures of all of the ERS PIs on the segments. Just to really highlight that, as a community, we will all enrich our understanding of the universe by learning how to use JWST and analyzing its data together. So thank you for your time and attention.